All right, so let's get prepared for the Unit 2A exam, multiple choice. So question number one, it says when one car travels 40 meters due east in 5 seconds and a second car travels 64 meters due west in 8 seconds. During their periods of travel, the cars definitely had the same. I remember this question, so I can go ahead and say average speed, but I'd like to prove it to you. So speed, first of all, it lacks direction. And since it lacks direction, then it can account for this idea that both of the cars were going in different directions. One was going east and one was going west. So because speed lacks direction, then that doesn't matter anymore. And then just know that v equals d over t. And in this case, the v means speed. So in the case of one car, it was going 40 meters due east in 5 seconds, and that is equal by ratio to the other car, which was going 64 meters west in 8 seconds. Both of those are coming out to be 8 meters a second. With this next question, I recommend labeling values so that it's easier to see the equation. So a race car starting from rest, that is VI, accelerates uniformly at a rate of 4.9 meters per second. What is the car's speed after it has traveled 200 meters? So you can see that the equation is going to be Vf squared equals Vi squared plus 2AD. Go ahead and rearrange this equation and then pause the video while you do that and then come back. Alright, so since we were just looking for the final speed, I just needed to take a square root of both sides. Now I'm going to plug in and solve. I'm getting 44.27. With sig figs, it looks like I get to keep 3, so I'll say 44.3. Alright, a rock falls from rest, a vertical distance of 0.72 meters, to the surface of a planet in 0.63 seconds. The magnitude of acceleration due to gravity on the planet. So just in case you were thinking, it is not 9.81, that's only the acceleration due to gravity on Earth. And I want you to pause the video while you think of an equation, and I'll think of an equation that works as well, and I'll come back and solve it. I settled on d equals VIT plus 1/2 AT squared, but I'm going to cross out VIT because I can see that VI is from rest, so that 0 would cancel that part out, and that means that really I'm just working with d equals 1/2 AT squared, and I am solving for A. So rearrange that equation and pause the video and rearrange that equation. So you get A equals d over 1/2 t squared. The distance is 0.72 meters. The time was 0.63 seconds. But remember to square that value and solve. Alright, so I got 3.63. But with sig figs I get to keep 2. Okay, next question. A car increases its speed from 9.6 meters per second to 11.2 meters per second in 4 seconds. The average acceleration of the car during this 4-second interval. So I think that the best equation to use here would just be the standard equation for acceleration, which is the change in v over t. And the change in v is going to be 11.2 minus 9.6. What's our VI and our VF? And the time is 4. And you'll get 0.4 meters per second squared. For this next question, where you're choosing a graph that best represents the relationship between the acceleration of an object falling freely near the surface of the Earth and the time that it falls, I would encourage you to consider that the acceleration due to gravity is 9.81 meters per second squared. And that value is constant as long as you're near the surface of the Earth. And that also means that the equation that the graph that you would choose if it's an acceleration versus time graph is you would choose a graph that does not change with time, because 9.81 meters per second squared is a constant. So I recommend choice 4 as your answer. 6. A rock falls from rest from a high cliff. So rest, that's VI, from a high cliff. How far has the rock fallen? So they're asking for a distance when its speed is 39.2. So that's VF, neglect friction. So we have VF, D, and VI. I think we can assume that we're on Earth, so we also have A. And an equation that I would recommend here would be VF squared equals VI squared plus 2AD. So I want you to rearrange this after pausing the video and solve for distance. So the first thing you should do is subtract the VI squared from both sides, so that you'll get VF squared minus VI squared equals 2AD. I'm still trying to isolate D. So D is VF squared minus VI squared over 2A. So I just divided by 2A on both sides. So plug in values now and solve. And I'm getting the height of that cliff as 78.3 meters. Okay, one more question. I'll do this one in red. It says a 1 kilogram ball. So by the way, this mass has no part in any of the equations we're using, so just cross it out. A 1 kilogram ball is dropped from the roof of a building 40 meters tall. So there's my distance. What's the approximate time of fall? They're asking me for a time. I think we can assume we're on planet Earth, and it's dropped from the roof, so its initial speed is 0. So with all that extra stuff that I put in, I'm thinking that the equation is going to be d equals VIT plus 1/2 AT squared, but I will drop out this section because the VI is 0, and it'll just be d equals 1/2 AT squared. And let's see, we are looking for time. So pause the video and isolate t. So I am dividing by 1/2 a on both sides, and that will cancel those items on the right. And then I'll just get that t squared is equal to d over 1/2 a. And in the last step, just take a square root of both sides, and then you can plug in values. The distance is 40 meters, and the acceleration is 9.81. So go ahead and solve, and you'll get, and I got 2.86 seconds, so that would be choice 1. In the 8th question, a cart travels with a constant, so that just means not changing, non-zero, which would mean not 0, acceleration along a straight line. Which graph best represents the relationship between the distance the cart travels and the time of travel? So if the cart is accelerating positively, then it would cover more and more distance as time went on. That's why I'm thinking that the answer is probably 1. I think the only other one that maybe would be reasonable would be this guy, but with a slope like this, it has this straight line, and the slope on this graph would be distance over time, so meters per second. Then this graph is saying that the velocity, that's meters per second, is constant. So if velocity is constant, then you can't have acceleration. It's one or the other. So I'm still going to go with choice 1 there. Number 9, it says the graph below shows the velocity of a race car moving along a straight line as a function of time. This graph is a velocity versus time graph, so I know that the slope is acceleration. But the question actually asks me for the magnitude of displacement. Displacement is measured in meters, so let me take a look at these axes again. And meters per second times seconds is meters. So that, to me, means I need to do an area under the curve, but only for this interval, the 2 to 4 interval. So I highlighted that interval right here, and I'd also like to point out that you should probably be thinking of this as a rectangle with a triangle on top. And keep in mind that the area equations for those two things are a bit different. For the triangle, the area is going to be 1/2 of base times height, and for the rectangle, it's going to be base times height. I'll plug in the values for those things now. The base of that triangle is 2 seconds wide, and the height of that triangle is 20 meters per second, or 40 minus 20. And the base of the rectangle also is 2 seconds wide, and the height of the rectangle is from 0 to 20 meters per second, so 20 meters per second. And this is going to yield 20, whereas this one yields 40. So overall, I'm seeing 60 meters. And the answer then would be choice 3. So similarly, this question asks me about a speed versus time graph, and it is asking me for acceleration this time. So since the unit for acceleration is meters per second squared, the best thing to do here is to find the slope, because it'll be meters per second over seconds. So the magnitude of the car's acceleration is going to be equal to its slope, and the slope here, let's see, change in y is going to be from 0 to 30, and the change in x is going to be from 0 to 3, and I'm getting 10 meters per second squared. Next, oh, this is an easy one, thank God. Which object has the greatest inertia? Inertia is measured only by proportionality with mass, so it has to be choice 4 because it has the largest mass. These values for speed do not matter. Okay, so a 2 kilogram body is initially traveling at a velocity of 40 meters per second east. If a constant force of 10 newtons due east is applied to the body for 5 seconds, the final speed of the body is. So normally I would suggest crossing this mass out, but I can see that since they're giving me a mass and the force, that is their way of asking me to solve for acceleration. So you may remember that there is an equation for acceleration which says that A equals F net over m, and the F net is the force they just cited. It's right there, so it's 10 newtons, and the mass is right here, 2 kilograms, and 10 over 2 is going to give me an acceleration of 5 meters per second squared. So now that I have the acceleration, check, I'll label other things in the question. So it's initially traveling at a velocity of 40 meters per second, so that's VI. And we have the force, and it's applied to the body for 5 seconds, so that's time. So at this point, we have an acceleration, an initial speed, and a time, and they want to know the final speed, VF. So this fits really nicely with the equation VF equals VI plus AT, and it's already set up to solve for VF, so I'll just go ahead and plug in. VI was 40, and the acceleration was solved for here, and it's 5. And the time that acceleration lasts is 5 seconds. So I just did that in my head, but it looks like 65 meters per second is going to be the final speed. Okay, number 13. If a 65 kilogram astronaut exerts I'll just label that, mass, exerts a force with a magnitude of 50 newtons on a satellite that she is repairing, the magnitude of the force, so they're asking me about force again, that the satellite exerts on her is, oh, this is a Newton's third law question. And Newton's third law says that every force has an equal and opposite reaction force. So if she puts a force of 50 newtons on the satellite, then the satellite puts a force of 50 newtons on her. All right, so in this question, we have a 20 Newton force due north and a 20 Newton force due east, and we're asked about equilibrium. Let me draw something for you. Basically, I'm just going to move the vertical axis over to the right, just mirror it. So there it is, I just moved it over. And I'm going to mirror the horizontal force as well. So what you can do with this is you can construct a hypotenuse really easily. So just go from the beginning to the end. And you can see which direction it's going. It's definitely going that direction. A little bit to the right and a little bit to the top. And we can also use the Pythagorean theorem at this point because we know that this side is 20 newtons. So we can use the Pythagorean theorem to solve for the hypotenuse or the resultant force. So I'm going to go ahead and say that a squared plus b squared equals c squared. But I want you guys to pause the video and solve for this. So after some careful math, you'll find that the value for c is 28 newtons. And the direction for that would be, let's see, northeast. But this question asks about equilibrium. And for equilibrium, we're going to need not the resultant force, but the equilibrant force. The equilibrant force is the force that you would apply to bring the system into equilibrium, and it could be defined as this force that I just drew in blue. It's going to be the force that sort of cancels the other forces. So that's the equilibrant in blue. And it would have the same magnitude as the resultant, and the resultant was 28 newtons, but it's just going to have an opposite direction. So it's still going to have a magnitude of 28 newtons, but the direction would be south and west. So 28 newtons southwest. Okay, next question. We have a soccer player kicking a ball. I'll label some stuff here. So it has an initial velocity of 10 meters per second at an angle of 30, so that's my theta. The magnitude of the horizontal component, I will call that VIX. So if you think of this one as a triangle, where theta is 30, and the initial velocity was 10 meters per second, we're looking for VIX, or just the part of that velocity that was horizontal. The easiest way to do that is to use the equation AX equals A cosine theta. And we'll just plug in the values that we have, but AX is A, which was 10, and the function is cosine, and the theta is 30. So solve for that and you'll have the answer. I got 8.66 meters per second. So choice 2 is looking good to me. Number 16 just asks which is a vector quantity, and vector has to include direction, so it cannot be speed. Mass does not have a direction. And work is similar to energy in that they're both measured in joules, and both work and joules are considered scalar quantities. So we are looking at displacement is our answer, because displacement does have direction. All right, so the next questions look like they go together. We have a soccer ball, and it's kicked at 25 meters per second at an angle of 40 above the horizontal. And number 17 asks for the maximum height that the ball reaches. So the thing that I like for you guys to remember when you're asked a question about maximum height is that you can say that the VF in that case is 0 meters per second. So let's go ahead and solve for that. We know that VF is 0. We know that A is going to be negative 9.81 meters per second squared. and we're looking for the distance or the height above the ground, and we know we can find the VI pretty easily from this diagram. There is a little bit of math I have to do, but I'll call it VIY because I just want the initial velocity in the y-axis, just the vertical part of its initial velocity. So I'll solve for that part now. In order to get the VIY, I'm going to use the equation AY equals A sine theta. And let's see, that's going to be 25 is my value for A, and then sine of theta is 40. So I'm getting, let's see, I'm getting an initial vertical component of speed, which is 16.1 meters per second. All right, so I have just to refresh, I have a VF, has to be 0, the acceleration is negative 9.81, the distance is what I'm looking for, and I have a VIY. So I think that the equation that I should use is VF squared equals VI squared plus 2AD, and I am looking for D. So let's rearrange this now. Remember that in the first part of this rearrangement, you subtract out the VI squared. So that's the very first part. And then you need to divide both sides by 2A. And then you have D equals VF squared minus VI squared over 2A. So I'm going to plug in now. The VF is 0, so it's going to be 0 minus. The VI squared is going to be 16.1 squared, and then over 2 by negative 9.81. And I'm going to solve that now. So I'm getting 13.2 meters. So I'll write that in here. And the next question, I was just previewing it, and it says that it wants me to calculate the magnitude of the vertical component of the ball's initial velocity. So that means they're asking me for the velocity initial vertical component. They're asking me for VIY. I already solved for that because I needed it in the last question. And VIY is 16.1 meters per second. And you can see my work over here on how to get it. So for numbers 19 and 20, they just want me to construct a resultant vector that represents the dog's total displacement. Displacement is the distance from the original position to the final position. So in essence, it's just a straight line from beginning to end. And the arrow would go that way. So that's my answer to 19. Check. And lastly, determine the magnitude of the dog's total displacement. I would recommend Pythagorean theorem here because that's a right angle. So I'll write that in and then we can solve that. So I did a little bit of calculation there, and I got to c equals the square root of 6 squared plus 8 squared, and that's going to give me a value of 10 for c, so 10 meters. And here's something that's kind of interesting. I don't know if it's going to help you a lot, but you probably remember from geometry that there's this thing called a 3, 4, 5 triangle. As long as there's a right angle involved, a triangle that has any combination of 2 out of these 3 sides, then you know the other side. So if it has sides 3 and 4, then the other side is 5, or if it has sides 3 and 5, the other side is 4. I think you see what I'm saying. But since there is such a thing as a 3, 4, 5 triangle, there is also such a thing as a 6, 8, 10 triangle. And I was just noticing that we have a triangle whose legs are 6 and 8, so I knew that the other side had to be 10. I don't think that it's actually a great way of showing your work, but it would, in a question like number 20, where all they ask you for you to do is determine, then I think it's acceptable to just say 10. And then you can just write 6, 8, 10 triangle. So number 21 looks like another soccer question. In this one, they want the horizontal component of the ball's initial velocity. So in other words, they're asking me for AX, or I guess you could say VIX, sort of depends on your language there. And here's my VI, it's 8.5. So I'm just going to say that AX equals A cos theta. A is 8.5. The function is cosine, and the theta is 35. So that means that my initial vertical velocity, so my initial horizontal velocity is, I got 6.96 meters per second, and after significant figures, you're going to get 7. I really have a love-hate relationship with this question right here. I love it because it shows deep understanding of these physics questions, and I hate it because it's a two-step question. There's just no way around it. I'll tell you why. It says approximately how far from the base of the cliff does the ball hit the ground? And I know that when it's asking me about how far from the base of the cliff, that it's a horizontal question. And I also know that horizontally, that the ball doesn't change its speed throughout its flight. It doesn't have any acceleration horizontally. And I know that also means that the equation I'll use ultimately to find the distance from the base of the cliff is just this equation that says v bar equals d over t. It lacks any reference to acceleration, and I will rearrange it so that it says that d equals v bar t. But their question here, because I can see that the v bar is going to be 25, but what is the t? What is the time that it'll be in the air as it's making its way down to the ground? So in order to figure that out, that is a free fall question, and it's all vertical as well. So I'm going to go ahead and label some of the pieces of information that I'm ultimately going to need. Let's see, the student is throwing a baseball horizontally at 25 meters per second. That's a VIX. It's not the VIY, which is the initial vertical velocity. The initial vertical velocity is actually going to be 0. So I actually do have a VIY, and I know that it's 0, and the reason for that is because the ball was thrown horizontally, which means that at least vertically it has no speed at all. And I also have a distance, which is 45. And we're on Earth, so I know that the acceleration is 9.81 meters per second squared. Let's use the equation d equals VIT plus 1/2 AT squared to solve for time. Now, normally the fact that I have time in two different parts of this equation would mean I would need the quadratic equation, but I really like that I can drop the VIT out because the initial vertical velocity, and this equation right here is all vertical stuff. It's just how long it takes for the ball to fall. There was no initial vertical velocity, so this part drops out. And the equation is going to be rewritten as d equals 1/2 AT squared, but I'm looking for t. So let's isolate t by dividing the 1/2 a on both sides so that it'll say t squared equals d over 1/2 a. And I'll take the square root of both sides as well. So to find the time, I'm going to have the square root of the distance, which is 45, over 1/2 a, which is 9.81 in this case. So let's solve that, and then that'll give us the time that we need. Alright, I solved it, and I'm getting about 3 seconds. It's 3.03. Let me just see. Yeah, I only get to keep 2 sig figs, so I will say 3 seconds. And then that's going to be a value that I then plug into the original equation that I knew I would need. And that original equation, if you just need a refresher, is d equals v over t, because if I want to know the distance that the ball hits from the ground, that's a constant average speed of 25 meters per second. So The v bar is 25, and now I know that the time that the ball spends in the air is 3. So my answer is 75 meters from the base of the cliff. 23. A .25 kilogram baseball is thrown upward with a speed of 30, neglecting friction. The maximum height reached by the ball is approximately. All right, so the mass in this case won't matter because I didn't see any forces, so I can't solve for some acceleration. But the ball is thrown upward with a speed of 30. That is going to be tricky because if the ball is thrown upward, then that means that the speed is going in a different direction than the acceleration. We're on Earth, I'm assuming, and the acceleration is negative. Especially the negative really matters when the VI is positive. So I'll keep going here. Neglecting friction, the maximum height. So we're looking for a distance reached by the baseball is. So when it reaches its maximum height, you also know the VF because the VF will be 0 at maximum height. So I actually know a great deal about this question, even though they only gave me one number that mattered for me. So I know the acceleration, I know the initial velocity, I know that I'm looking for distance, and I know the final velocity. So the best equation here is going to be VF squared equals VI squared plus 2AD. And I am looking for D, so let's rearrange the equation. So in the first step of my transformation, I just moved the VI squared over to the left using subtraction. And in the second step, I moved the 2A to the left using division. I can plug in now the VF is 0 because it's going to be motionless at the top of its flight. The initial velocity was 30, but don't forget to square that value. And the acceleration is going to be, this is important, negative 9.81 meters per second. So let's solve. All right, I got an answer of 45. Well, maybe it's 40. It's 45.8. How many sig figs? I get 2. So I'll go with 46 meters. There it is. All right, 24. An outfielder throws a baseball to the first baseman at a speed of 19.6 meters per second and an angle of 30 above the horizontal. Here's my angle. The speed is 19.6. Which pair represents the initial horizontal velocity and the initial vertical velocity? So the equations that you're going to use are, if this is AY and this is AX, then AY equals A sine theta, which in this case is going to be 19.6 sine 30, and AX is going to be A cosine theta, which in this case is 19.6 cosine of 30. So let's solve for that now. So the values I got were 9.8 for AY and 17 for AX. That actually looks like choice 1 to me. Okay, 25, last question on this page. It says a golf ball is hit at an angle of 45 degrees above the horizontal. What is the acceleration of the golf ball at the highest point in its trajectory? The first thing I have to say about this is trick question. The acceleration of the golf ball at the highest point in its trajectory is going to be the acceleration of the golf ball at any point in its trajectory. The acceleration of the golf ball is due to Earth's gravitational field, so it's going to be 9.81 meters per second squared. That, by the way, is downward. Okay, we're in the home stretch. A volleyball hit into the air has an initial speed of 10 meters per second. Which vector best represents the angle above the horizontal that the ball should be hit to remain in the air for the greatest amount of time? All right, so if the goal is for the ball to remain in the air for the greatest amount of time, then it needs to be hit at a very large angle. I think the best answer there is going to be choice 1. Even though the ball won't really go anywhere in the horizontal direction, it seems like it's going to land exactly where it was launched. It will spend the most time in the air. And the reason for that is because as the launch angle theta is increased, what you're doing is you're increasing the a y component of the vector. Therefore, it's going to have the largest initial velocity in the vertical direction, and it will spend the most time in the air. Okay, 27. A basketball player jumped straight up to grab a rebound. If she was in the air for 0.8 seconds, how high did she jump? I could solve for her initial velocity, and then I could use an equation like vf squared equals vi squared plus 2ad to find the distance that she jumped, but that would make it a two-step question. So I can show you how to do that in class if you want me to. But the only way I can think of to make this a one-step question, I made a reference to it in my notes, and it's to use the equation d equals vit plus 1/2 at squared, but it's gonna need you to make some special dispensations with your logic. So just know that when she's in the air, she goes up and then she goes down, and the two halves of her flight are the same, they're just opposite. So you can sort of split this flight into a first half and a second half. The distance will be the same for both because it's going up to this height right here. What I'm going to suggest is that we focus in on the second half of her flight. So just the part on the right there. And we're going to solve for basically the fall of her flight. So not the rise, but the fall. And that's going to mean that the initial velocity, if we're solving for fall, let's see, d equals, the initial velocity will be 0, and regardless of the time, that's going to drop out. So it's only if we're starting from the top that the initial velocity is 0. So initial velocity is 0 if you start from the top, so that part drops out. So plus 1/2 a. A is going to be 9.81 for the gravity of Earth, and t squared. So one thing I noticed was that they said that she spends 0.8 seconds in the air, and that's her total time in the air. So instead of writing 0.8, I suggest that we write 0.4, and that is going to be squared. So let's solve for that now. I got 0.78 meters as the height of her rise, but also the distance of her fall. Okay, so it says 28 through 30 are all based on this diagram. So it's launched with it's a cannonball launched at an initial speed of vi and a launch angle of 30. It looks like that stuff's here. And it does land on the ground 2 seconds later, so the total time in the air is 2. On the diagram above, sketch the ideal path. All right, ideal means neglecting friction. So the ideal path would be parabolic. I'm not the world's greatest artist, but a parabola looks something like that. It should have like a vertical axis that it reflects itself on both sides. I think that looks pretty good. All right, so 29. How does the total horizontal distance traveled by the projectile change as the launch angle is increased from 30 to 45? So here's the thing. 45 degrees is going to give you the maximum range. So if 45 degrees is the maximum range and 30 is less than that, then that means that the total horizontal distance traveled as you increase the angle from 30 to 45, it has to increase. That's my answer. How does the maximum altitude of the projectile change as the launch angle is increased from 30 to 45? So at 30 degrees, the maximum height that it reaches is going to be rather shallow. But as I increase it to 45, I'm going to be increasing the value for VIY as theta increases. So I'm increasing theta, so I'm increasing the value for VIY, which is going to give me a larger altitude as well. So my final answer is that the altitude increases. All right, my last three questions are based on this diagram. It says a projectile is fired from the ground with an initial velocity of 250 meters per second at an angle of 60. And then question 31 says, on the diagram above, use a protractor and a ruler to draw a vector to represent the initial velocity of the projectile. It says, begin the vector at point P and use a scale of 1 centimeter equals 50 meters per second. Okay, so one disadvantage of this this program is that I do not have a protractor or a ruler in the program. So I may need to help you guys reproduce this in class. But use your protractor to get an angle of 60 degrees right here against the horizontal. So make sure that angle is 60. And then you need to use a scale of 1 to 50. And it says that the speed is 250. So I think that if you do 250 over 5, you'll get, 250 over 50, then you'll get 5 centimeters. So the length of the vector needs to be 5 centimeters long. So I'm just going to throw in a line here. I have no idea if this is correct or not, guys. But your line needs to be exactly 5 centimeters long, as close as possible, and then 60 degrees above the horizontal. So use a protractor to get this angle correct, and use a ruler to get that distance correct. So let's just say that I did it, and then that part's done. And it says, explain why the projectile has no acceleration in the horizontal direction. The reason for that is because accelerations are caused by forces, and after the initial launch, there is no horizontal force, and therefore there can't be horizontal acceleration. And that, of course, is based on Newton's second law, which says that A equals F net over m. So a lack of force is going to have a lack of acceleration. Last question, determine the horizontal component of the initial velocity. Let's use the equation ax equals a cosine theta, where a is 250 meters per second, and cosine is the function, and theta is 60. Let's solve. I got 125 meters per second as my initial horizontal component. And that concludes the review sheet. I will flip to the next slides just so that you can see your answer key and check to see if I made any mistakes.